Welcome to this video, where we dive into an exciting new approach in the world of vision transformers, SimA, simple Softmax-Free attention for vision transformers. We're going to explore how this approach makes transformers more efficient, especially on devices with limited power, like the Raspberry Pi. Whether you're a college student interested in AI or a working professional wanting to stay updated, this video will help you understand the core ideas behind SimA in a simple and engaging way. Let's start with the basics. Vision transformers are powerful tools for computer vision, offering great accuracy compared to traditional convolutional neural networks. They work by splitting an image into smaller pieces called tokens and applying attention mechanisms to figure out which parts of an image are important. But there's a catch. The main attention mechanism, which uses a softmax function, can be computationally expensive, especially for smaller devices like edge devices. This is where SimA comes in. It simplifies things by removing the softmax layer, making transformers faster and more efficient. So, why is softmax such an issue? Essentially, softmax involves exponential calculations that make it quite slow. Imagine trying to run a vision transformer on your phone or a small edge device. All those expensive calculations add up quickly and slow things down. For example, when measuring run time on devices like the Raspberry Pi or NVIDIA Jetson Nano, softmax ends up consuming more time than other parts of the attention block. The softmax function works by taking the exponential of each value in a vector and then normalizing it by the sum of all exponentials. This ensures that the output values are between 0 and 1, and that they all add up to 1. While this is effective for attention mechanisms, the exponential operation is computationally expensive, especially on devices with limited processing power. As a result, the softmax function becomes a bottleneck for running vision transformers efficiently on such devices. The SimA model aims to solve this problem by getting rid of softmax. Instead, it normalizes the input matrices known as query and key using a simple L1 norm. What does this mean? Basically, it's like applying a much simpler operation to make the calculations more manageable. This way, the attention mechanism can focus more on finding relationships within the image without the computational burden of the softmax function. The L1 norm is a simpler way to normalize data by summing the absolute values of elements in a vector and then dividing each element by this sum. By using the L1 norm to normalize the query and key matrices, SimA ensures that the resulting attention values are still appropriately scaled, but without the need for the costly exponential calculations. This makes SimA a more efficient alternative, especially for devices with limited resources. Let's break down how SimA works. In a traditional attention mechanism, the query and key matrices are used to calculate how much one part of an image should pay attention to another part. Softmax is used to ensure these attention values are normalized, but SimA does it differently. It just scales these matrices using the L1 norm, which is computationally much cheaper. This might sound like a small change, but the impact is huge. By normalizing query and key matrices before multiplying them, SimA simplifies the entire attention calculation into just 3 matrix multiplications. This significantly reduces the computational load, making the transformer work more smoothly on smaller devices. To understand this better, let's compare the two approaches. In the traditional attention mechanism, the query matrix and the key matrix are multiplied to produce an intermediate matrix that represents the attention scores between different parts of the input image. These scores are then passed through the softmax function, which normalizes them. Finally, this normalized matrix is multiplied by the value matrix to produce the output. In SimA, the query and key matrices are normalized using the L1 norm before they are multiplied. This means that the resulting attention scores do not need further normalization using softmax. Instead, they can be directly used in the next step, which is multiplying by the value matrix. This reduces the computational complexity and makes the entire process faster. Let's talk about how SimA compares to other linear attention methods. Linear attention methods aim to reduce the computational complexity of the traditional attention mechanism, often by approximating the softmax operation or by using alternative kernels. SimA is similar in its goal of reducing computational overhead, but takes a different approach by eliminating softmax entirely. One well-known linear attention method is Performer, which approximates softmax using random feature mappings. While this approach does reduce complexity, it still involves additional operations that can be computationally heavy, especially for devices with limited power. In contrast, SimA keeps things simple by using L1 normalization, resulting in fewer computations and better efficiency on small devices. Another method, Linformer, approximates the attention matrix using low-rank projections to achieve linear complexity. However, Linformer's performance can degrade with certain input types, and it introduces additional complexity in the form of matrix factorization. SimA, on the other hand, retains high accuracy without these approximations, making it a more robust option for different kinds of vision tasks. Overall, SimA offers an efficient and straightforward alternative to traditional and linear attention mechanisms by eliminating the need for softmax and using simple normalization techniques. This makes it well suited for applications requiring both high performance and low computational cost. Another cool thing about SimA is that it can work well even with a simplified attention setup. Vision transformers usually use something called multi-head attention, which means splitting the attention into multiple parallel parts, or heads, to focus on different parts of the image. But SimA works almost just as well, even when this is reduced to a single head, further reducing computational complexity without sacrificing much in terms of accuracy. In traditional vision transformers, multi-head attention is used to allow the model to focus on different aspects of the input simultaneously. Each head processes the information independently, and the outputs are then combined to form the final attention output. This approach helps capture complex relationships in the data, but also increases the computational cost. SimA, however, can achieve similar performance with just a single head. This is because the L1 normalization makes the attention scores more stable and comparable across different tokens. As a result, even a single head can effectively capture the important relationships in the image, which simplifies the model and reduces the number of computations required. Okay, so what does all this mean in practice? The researchers tested SimA with 3 different types of vision transformers, DEIT, CVT, and XCIT. Another key benefit of SimA is its flexibility. The attention mechanism in SimA can dynamically adjust the order of computations based on the number of tokens and the number of channels. Depending on the size of the input image or the model's architecture, SimA can choose the optimal computation order to further improve efficiency. This dynamic adaptability makes SimA a versatile solution for various types of vision transformers. To wrap it up, SimA stands for simple attention, and it really lives up to its name. By removing the costly softmax operation and using simple normalization techniques, SimA makes vision transformers faster and more efficient, especially for edge devices. It's a promising step towards making AI more practical in everyday settings where computing power is limited. The key takeaway here is that simplicity can lead to significant improvements. By rethinking the way we handle attention in vision transformers, the researchers behind SimA have shown that we can maintain high accuracy while reducing computational complexity. This opens up new possibilities for deploying AI on a wider range of devices, from smartphones to drones to IoT sensors. If you found this video interesting, Don't forget to like and subscribe for more AI content, explained in simple terms. And if you have questions or topics you'd like me to cover, drop a comment below. Let's make AI knowledge accessible to everyone. Thank you for watching, and see you in the next video.